I'm Timothy Tan, and I teach a variety of subjects here at NIE, mostly in the science and technology areas. These include biology, biotechnology, and genetics, and computer applications for secondary level. I kind of teach a very broad spectrum of subjects, but that's what I like. I'm very keen on integrating across several subject areas, and I like this idea of being able to cross-pollinate ideas whenever I can. So you could say that I like to get my hands dirty, doing things whenever I can, do it for myself. And I guess that really influences the way I approach science. It's really important to me that I guess I impart the sense that science must be something that is done hands-on, with the core idea not being just that you do it, but you do it with a strong sense of what you're trying to do. In other words, not just hands-on, but minds-on. And when we do that, our ability to learn science is so much stronger. You learn concepts that go beyond the textbook. Taking a hands-on approach just makes science so much more fun. And fun being an important operative word when we're trying to learn. We all know, obviously, if you're having fun, you're going to learn it better, you're going to enjoy yourself. If you can learn something because you want to learn it and because it's so interesting, then I think that's more than half the battle won in any subject. So what is technology? That's a word that has, hundreds of definitions. But I think the simplest way to look at it would be that technology is just the applied use of knowledge, particularly scientific knowledge. So it could be as simple as a lever or wheel. These are forms of technology just from really, really long time ago. So a scientific tool, scientific instrument, is really something where the technology just allows us to sense or measure something that our five senses cannot naturally do. So it's to see things that we would not otherwise be able to see, hear things that we would not otherwise be able to hear, sense, touch, or determine, for example, the temperature of something or how much oxygen there is somewhere. So you are probably familiar with scientific instruments. In school, you'd go to a science practical and you'd make use of, say, a microscope, or you'd use a thermometer. Very often we don't think too hard about what's going on in there, how it works. So what I think is, in some ways, you should really look at the instruments in front of you when you have the opportunity. And in a sense, carefully, safely, play with them. Not only measure what you're supposed to, but then think about what it's actually doing, and if you could possibly even conduct your own little investigation while you're at it. With just a little bit more thought, you could possibly even build your own instruments. Because once you fundamentally understand how they work, what's the science behind a scientific instrument, then you have all the pieces necessary to really think about putting them together. And from that gives you the opportunity to innovate. Building your own instruments is really a core scientific tradition. So Galileo made his own telescopes. The tools weren't readily available. They'd been discovered just very recently at that point in time, and he just heard about what telescopes were. He refined it over several iterations. They got better and better, even better than the original inventors of the telescope were able to achieve. That allowed him to make a series of groundbreaking discoveries about the cosmos and the nature of the universe around us. Understanding how scientific instruments work, how they work together, because you made them, really gets to the heart of science. It leads you towards an understanding of the epistemology of science. So what is epistemology? Epistemology is just very simply how we know what we know. So we live in an era when a lot of scientific knowledge is really just handed to you. You're just told, and you're bombarded with a lot of information that sometimes, to a certain extent, it's a bit difficult to figure out who to believe, right? So because you're doing it hands-on, because you're gathering your own data, and if you have to share that data, you're engaging in so many of the phases of, and so many of the aspects of real scientific work, real scientific research. Learning science this way becomes more than just memorizing a bunch of facts. It really becomes an experience. It becomes a way of doing things. It's a way of knowing things. I want to show you something cool. I've been playing with this for a few years now, and it's basically a way of exploring the microscopic world within a droplet of pond water. So what is a microscope? Like a telescope, it's a scientific instrument that helps us see something we would not otherwise be able to do with our naked eyes. Now, I'm sure microscopes you've encountered, like those in a school laboratory, look like fancy pieces of equipment, kind of difficult to tell how it works, but really the principle behind it is that it is a tool that helps us see something we can't. I think it's really worthwhile to put together your own microscope, because when you do so, you really engage with the way this device works. Now, it doesn't have to be a complex optical microscope. All it needs to be is a device that allows you to make really useful observations. And all you really need is a laser pointer and a syringe. You need some pond water. Don't need a lot of it. This looks a little bit complicated, but it's really just holding the syringe and the laser pointer at right angles to each other so that we can hold a droplet of pond water in the beam of the laser pointer. So the laser dot becomes a much larger circle of light. And in that circle of light, you may actually see microorganisms that are within that droplet of pond water. Obviously, this isn't a high-tech piece of equipment, but if you stop and think about it, many of our scientific tools, our scientific instruments, actually do the same thing. It's some representation of the phenomenon being studied. Other kinds of microscopes may use similar principles. The microscopes that you may be familiar with use optics to visualize the microbes in the droplet of pond water that's on a slide. There are other kinds of microscopes such as electron microscopes. There's even microscopes that make use of ultrasound to image the very fine cracks that may occur in aircraft parts. So in a laser pointer microscope, you're just seeing the shadows cast by microorganisms in the pond water. But that's enough to tell you about some of the shape, the type perhaps. All that a good scientific instrument really is a device that lets you choose exactly what you want to study and allows you to observe that phenomenon in a very simple way. When you're toying around in the lab, I think one thing you should always do is keep a notebook. Whether it's recording the data and your observations that you've made, ideas that you have for the next thing to do, questions that you have, designs for your next device or instrument, or anything that you want to make. All of these things would be really good if you wrote them down in a dedicated journal or notebook. Keeping a scientific notebook really is part of the traditional process, the traditional approach to doing research. It's important because you need to show that you've done the work. You need to record data systematically. This enables the data to be verified, to be double-checked. And in fact, very simply put, it helps you remember what you've done. Even your mistakes become important because errors, mistakes, data that was perhaps not what you expected it to be, could actually be the breakthrough you're interested in. It could actually lead to innovation. It could actually lead to the next scientific discovery. I'm sure you're familiar with this idea that an expert is someone who is a specialist in an area. When you get into a particular field or pick up a career, the aim usually is to become more knowledgeable about a shrinking, smaller area in that field. But in many ways, it's actually now more valuable to be a generalist. And I don't mean just knowing a little bit about everything, but being able to integrate across domains of knowledge. That means not just being a specialist in one area, but knowing a fair amount about different areas. Being too specialized in any one particular area can sometimes put blinders on your ability to make connections between disciplines. It's now very well known that scientific discoveries, technological innovations are all now focused in the areas between the traditional boundaries of disciplines, the gaps between domains of knowledge. The way I see it, when you get hands-on with real-world science, that really gets you thinking about how knowledge connects, how different pieces of information, perhaps from very different disciplines, actually come together and interact in the real world. So that approach makes you think about scientific knowledge less in terms of answers to a quiz, but much more about science as understanding the world around you. Science can actually seem very intimidating because it almost feels like you have to be an expert in that area before you can begin to contribute something. That the questions that you have aren't important or are inconsequential simply because, well, you might be thinking, what do I know, right? I'm just a novice. But I think many of the questions in this world are actually best asked by the novice. The novice can actually ask far more consequential, far more fundamental questions that the expert might overlook. It is sometimes the novice that asks the silly question, the question that essentially the expert might one day turn around and say, now why didn't I think of that?